Good afternoon. Thank you for coming to this wonderful event. And I want to thank the JapanPrize Foundation and the selection committee for selecting me to win the 2025 JapanPrize for Material Science and Production. There are many people in this audience who've contributed to this technology, so I beg their pardon if I don't mention their work in my presentation today. So today I would like to give my personal view of the development of metalorganic chemical vapor deposition for 3,5 compound semiconductors. And what you see on this slide in the upper your left is a picture of a reactor I built in 1975 at Rockwell International. This was a handmade, hand-designed reactor that grew on basically 1 2-inch diameter wafer operating at atmospheric pressure. The middle picture is a commercial reactor made by a company in England, Thomas Swan Limited, in around 2000. This was one of the first production reactors that were developed for producing large-scale MOCVD devices. The bottom photograph is the current generation 2025 Taiyo Nippon Senso production reactor. And you can see over this 50-year period, dramatic changes have occurred in the quality and the size of these reactors. And fortunately for me, I had a chance to work on this over this 50-year period with a variety of tools, some of which I made, some of which I purchased. The bottom line is that in the current generation reactors, they're much more uniform, much more efficient, and contribute greatly to higher quality epitaxy. Let me begin with a short outline of what I intend to cover today. First, I'll describe the development of 3,5 compound semiconductors, describe the MOCVD process and epitaxial reactors. Then I'll move into the device applications. The first MOCVD-grown device was actually a solar cell that we made in 1977. Injection lasers were also made by my team the same year. And then we developed the next generation of laser diode, the quantum well laser diode. I'll describe that briefly and go into the development of light-emitting diodes in the current generation of devices and the market that has been developed for light-emitting diodes grown by MOCVD. Next, I'll describe power device applications and then speculate on the future impact of the MOCVD epitaxial materials technology. I've selected 10 technologies that I believe change the world that relate to materials and processes. I believe these underpin society's progress. That is, material science and production are coupled to the advancement of society. First of all, control of fire, then the creation of stone tools, next bronze tools, then iron tools, so the Iron Age. Then we moved into a new area, the control of electricity, which allowed us to distribute power and make our lives much better. And so we developed the first generators that could generate electricity in a controlled way. Then the steam engine, the internal combustion engine for good or evil, the vacuum tube, the semiconductor, and later we'll see about the artificial intelligence. Basically, what I'm trying to describe here is this transition of materials and technology that has advanced our society. We still, of course, don't know how artificial intelligence is going to impact us, but they certainly represent inflection points in the history of our society. I'm going to focus on the semiconductor in this talk. Obviously, semiconductor enables AI, so this is the only exception in this list that what is following actually depends on what precedes it. So in the other cases, these were replacement technologies. In this case, these are enhancement technologies. That is, AI will enhance semiconductors and also the other way around. Let me turn to the development of interest in 3-5 compound semiconductors. I'm sure all of you are familiar with the periodic table and classical silicon and germanium semiconductors, which are crystals with a diamond lattice. If you replace the column 4 elements with equal molar fractions of elements from columns 3 and 5, and you arrange them on a zinc blende lattice, you can create the compound semiconductors, commonly referred to as the 3-5s. Gallium arsenide being the prototypical idea behind combining these elements. If we replace some arsenic atoms with phosphorus, we create a ternary alloy, gallium arsenide phosphide. This was the first ternary alloy to be used to make visible light-emitting diodes. If we replace some gallium atoms with aluminum, we can create the quaternary aluminum gallium arsenide phosphide, which was the first quaternary semiconductor ever made. If we substitute indium for gallium, for example, we can make indium gallium arsenide, indium gallium phosphide. We could also make the quaternary aluminum gallium indium phosphide, which is used for the red and yellow and amber light-emitting diodes we all use today. We can also exploit the properties of the elements antimony, nitrogen, and boron to create a variety of compound semiconductors, all based on column 3 and column 5. These 8 elements are the ones that primarily we're using today for all of our 3-5 device technologies. And all of these can be grown by MOCVD. The semiconductor market is rapidly increasing. The global silicon semiconductor market size was valued at around $630 billion in 2024, with a projected double-digit market growth rate for 2025. The global 3-5 compound semiconductor market was valued at about $54 billion in 2024 and is projected to reach $154.5 billion by 2034 in the coming 10-year period, with a compound annual growth rate of about 11.2%. So these are not small markets, and clearly the elephant in the room is silicon, with a value of about $630 billion now. And 3-5's much smaller, but as you can see, both of these creatures are animals. They're both mammals, and the elephant is certainly powerful and intelligent, but the young lady is more intelligent, she's more flexible, and certainly more clever than the elephant, and I can expect that she'll contribute more to our society in many different ways that an elephant cannot. So by this analogy, I'm betting on the young lady. The global MOCVD materials market was about $1.1 billion in 2023, growing at a compound annual growth rate of about 9.7% over 10 years to be about $2.8 billion in 2030. The lower panel shows a pie chart of the use of these materials by market sector application, and you can see that consumer electronics is by far the largest, with automotive being important, as well as defense and other applications. In particular, we expect telecom to continue to grow dramatically as we more and more rely on the World Wide Web for our information and interaction with ChatGPT and other types of AI servers. GaN plays an important role. Gallium nitride plays an important role in this space, and so does gallium arsenide, with indium phosphide and other materials being the third component of this growth over the next 10 years. Let me turn now to the question of how can compound semiconductors composed of 3-5 elements compete with silicon. Silicon devices are widely used due to their low cost, availability, and well-established manufacturing processes. They are certainly ideal for general-purpose electronics such as microprocessors and memory chips. So the Swiss Army knife for silicon has many blades for solar cells, integrated circuits, power devices, photodetectors, silicon photonics, and sensors. So it's a quite capable material, and this particular Swiss Army knife will cost you today $24 on the web. The Swiss Army knife for 3-5 semiconductors, I believe, is much more flexible, has more applications, and offers higher performance. So this is my view of the Swiss Army knife for 3.5 semiconductors. It has blades for light-emitting diodes, laser diodes, LiDAR radar, solar cells, photodetectors, thermal photovoltaics, radio frequency electronics, lightwave modulators, power electronics, photonic integrated circuits, and sources for silicon photonics. This Swiss Army knife is for sale today for $1,000, but it's worth every penny of it, as you can see. Let me now turn to another important element in our discussion today, and that is what created the interest in semiconductors. After all, for many years they were known to be difficult materials. In fact, Wolfgang Pauli at one point said he didn't think semiconductors existed. But in 1947, the transistor was invented by John Bardeen and Walter Brattain at Bell Telephone Laboratories, and this changed the semiconductor from a curiosity, a laboratory curiosity, to an industry. This work was also important in that Bardeen identified minority carrier injection as an important process in a semiconductor for the first time. The first point contact transistor wasn't very pretty. It was composed of a piece of plexiglass placed on a piece of recycled germanium, but it created the interest in making solid-state amplifiers. And this led to very quickly the development of the NPN bipolar junction transistor, which was invented a year later, actually a few months later, in January of 1948 by William Shockley, who developed the theoretical models for the NPN and PNP bipolar junction transistors. This device required control of doping concentrations in all three layers, leading to the development of demand for precise control of small concentrations of impurities, which led to the development of epitaxial growth. So using this timeline, I'll try to describe how epitaxial growth created our ability to make these compound semiconductor alloy materials. As I mentioned, in the 1940s, semiconductors were just being discovered and studied. The first PN junction was made by accident by an engineer named Russell All at Bell Telephone Holmdel, and his PN junction was in silicon. As I mentioned, in 1947, Bardeen and Brattain invented the germanium point contact transistor, and then Shockley added the NPN and PNP structures, which we now commonly use in all of our transistors. In 1950, two workers, one in Germany, Hans Welker, another in the Soviet Union, Nina Goronova, understood for the first time that column 3 and column 5 elements could be combined to make semiconductors. So this is the birth of the 3.5 semiconductor that we all use today. In 1960-61, because of the interest in controlling doping in silicon and germanium, vapor phase epitaxy was developed over this one-year period for both silicon and germanium, but also gallium arsenide, indium arsenide, and importantly, the ternary alloy gallium arsenide phosphide by Nick Holniak at General Electric at the time. And that was used to make the first visible red light-emitting diodes. Also, a year later, or 2 years later, in 1963, liquid phase epitaxy was developed for gallium arsenide. So this work sets the stage for the next development. In 1962, 4 important results were reported for 3.5 compound semiconductor optical devices. First, high-efficiency infrared gallium arsenide LEDs were reported by Bob Redeker's group at MIT Lincoln Laboratories. And later that same year, in 1962, Robert Hall at General Electric in Schenectady demonstrated the first infrared laser diode. As I mentioned, Professor Holniak developed the first red LED that was commercialized in 1963. And also in 1962, a few months after the first injection laser in gallium arsenide, Professor Holniak demonstrated the first injection laser in gallium arsenide phosphide, which at 77 Kelvin emitted in the red. So this is the beginning of the semiconductor laser diode. This development of epitaxial growth led to rapid development in the period 1967 to 1970 to the development of heterostructure devices using liquid phase epitaxy, for example, for laser diodes, and heterostructure solar cells in gallium arsenide. Also in this time frame, MOCVD was developed in 1968 and MBE about 11 months later in 1968. The next period saw rapid development of the use of epitaxy for the growth of semiconductors, including the first quaternaries, aluminum gallium arsenide phosphide in 1970 by LPE, indium gallium arsenide phosphide in 1976 by LPE, and aluminum indium gallium phosphide in 1981 by MBE, and then a year later by MOCVD. These developments along this timeline created what I call the basis of the Cambrian explosion equivalent of solid-state devices in the 1980s and 1990s. So using these tools of epitaxial growth and materials design, material science, we were able to expand the types of devices and the functionality of devices that are being made and sold. As I mentioned, Professor Holniak's work in the 1960 to 62 period led to the first visible light-emitting diodes. This work was begun in early 1960, and in 1962, he had demonstrated the first laser. Shown in this picture on the left is a gallium arsenide phosphide crystal he had grown by vapor phase epitaxy. It is polycrystalline. The crystal is laying on a US penny, so it is less than 1 centimeter in length, but it has naturally occurring facets, which were growing inside the ampule, which he used to orient to make the facets for his laser diode. And what you see in this upper part of this picture is his first laser diode mounted on a header. On the right side, you see Professor Holniak in 1962 examining one of his laser diodes. I wouldn't recommend doing this today because your laser is too powerful. But at this time, this was in pulsed operation and very low duty cycles. As I mentioned, he received the JapanPrize in 1995 for his work on semiconductor materials and devices. Professor Holniak's red LEDs were the first commercially available LEDs in the world. GE commercialized them in 1963. The original price for a red laser diode was $2,600 in 1963 money, and $700 for a single red LED. These devices were about twice as expensive as the infrared gallium arsenide devices that GE also sold. The gallium arsenide IR lasers and gallium arsenide phosphide red devices were sold in 1965. They appeared in the Allied Industrial Catalog you see on the right. A gallium arsenide IR LED was $45 a piece, and the laser diode was $650 a piece. The gallium arsenide phosphide red laser diode was deemed to be twice as valuable, so its cost was $1,300 each, and the gallium arsenide phosphide red LED was $135 each. If you translate that to today's dollars, each LED would cost you $1,400. So imagine having a sign somewhere with that kind of component in it. Today, a much brighter gallium arsenide phosphide red LED costs about 2 cents in today's dollars, a factor of 70,000 less than today's $1,400 inflated price. So dramatic reductions in cost and improvement in performance. Let me now turn to the next important event, which was, as I mentioned, the development of the quaternaries. This is the energy gap in electron volts versus lattice constant in angstroms for the quaternary aluminum indium gallium phosphide, which can be grown lattice matched to gallium arsenide substrates, as shown by this vertical line. Materials along this vertical line can be produced in high quality on gallium arsenide substrates and are used currently to make high brightness red LEDs, amber or orange LEDs, yellow LEDs, but it cannot be used to make green LEDs because of the proximity of the indirect band gap section of this quaternary alloy shown here in dotted area. So we have to turn to another material to make green and blue LEDs. The first growth of this quaternary was by MBE, by Asahi and others at NTT in 1981, and the MOCVD was first used to grow this quaternary by Hino at NEC in 1983. So the Japan effort has led this quaternary development for many years. The other quaternary of very extreme interest is the aluminum indium gallium nitride quaternary, shown here again in band gap energy versus lattice constant for these wurtzite crystals. These are all direct band gap alloys and binaries, with the endpoints being about 0.7 eV for indium nitride and then the ultraviolet 6.2 EV for aluminum nitride. So this quaternary can easily cover the important spectral regions of green, blue, and ultraviolet LEDs and laser diodes, and being actively researched today throughout the world. Aluminum gallium nitride, the ternary, was first grown by MOCVD by Kahn et al. At APA Optics in the United States in 1983, and indium gallium nitride was first grown by Matsuoka, who's here in the audience, at NTT in 1989. Let me now turn to the application of this process technology to the development of better reactors and hopefully improved understanding of the process itself. MOCVD was actually invented by Dr. Hal Manasevit, who demonstrated the first growth of gallium arsenide by MOCVD in 1967. At that time, he was working for North American Aviation, famous aircraft company, which later became Rockwell International in Anaheim, California. He published his first work on the growth of gallium arsenide on sapphire in January of 1968, and his first work on the growth of gallium nitride on sapphire in 1971. Manasevit, who was a chemist, was interested in insulating single crystal semiconductors on insulating substrates, and developed the growth on a variety of substrates, including diamond spinels and beryllium oxide. This photograph is of Hal in around 1960 when he began his work, and this is a picture of Hal about 1975 when I first got to know him. MOCVD is a relatively simple process in the chemistry point of view, but in a practical sense is quite complex to control. So we typically use stainless steel growth chambers that are operating at low pressure, typically 1/10 of an atmosphere in a hydrogen-nitrogen atmosphere. We begin with a heated susceptor that upon which a substrate is placed, and then we inject our precursors after heating to 1,000 degrees or so. In this case, trimethyl gallium, which is a gallium atom with 3 methyl radicals attached. We inject that vapor into the reactor. It diffuses to the growth surface and pyrolyzes in the high temperature region above the substrate. And next we inject ammonia, NH3, simple molecule, nitrogen-3 hydrogen atoms. That also pyrolyzes in this environment, and atomic diffusion occurs to the surface through a boundary layer, which eventually leads to the formation of covalent bonds incorporating gallium and nitrogen into the crystal. So step by step, we create a film of gallium nitride with 3 methyl radicals as our byproduct, which is swept out in the exhaust stream because this compound is stable at these temperatures around 1,000 degrees. So we begin with a layer of gallium typically, and then add nitrogen, gallium, nitrogen, etc., layer by layer, growing this crystal. In this particular case, it's a wurtzite crystal, and can be used to grow the quaternary. If you replace gallium with aluminum and or indium, you can create a quaternary or a ternary. This is an example of an indium gallium nitride ternary layer excited by light showing that LED emission can be achieved. This is a photograph of one of my early reactors, not the very first one I built, but one approximately from April 1976 when this photograph was taken. It's an atmospheric pressure reactor, small quartz vertical chamber, 2-inch diameter susceptor. It has some innovations, including metal seal low dead volume switching valves to switch the precursors in and out of the reactor stream, improved system integrity, including the use of all welded metal sealed bubblers for the metal organic sources like trimethyl gallium and trimethyl aluminum, which are shown here. Because we were limited in finances, my temperature baths were ice to control the gallium temperature and room temperature to control the aluminum temperature. We had no constant temperature baths. We also had diethyl zinc for P-type zinc doping. And I built this beautiful little box to control the valves so I could switch multiple valves at one time to create abrupt interfaces. So this is a very useful tool at that time frame, but it's now 50 years old and we have much better tools. Let me now describe how that occurred in a very simple way, at least. Beginning in 1967, as I mentioned, Dr. Manasevit had been using vertical quartz chambers like this, like is shown here, for the growth of silicon, and he simply adapted that for the growth of gallium arsenide on sapphire. And in a reasonably short time, other people began to explore this technology. Sidney Bass in the UK developed what was called the Bass cell in 1975. It's a horizontal reactor, as you can see. Another important event that occurred in 1978 was Jean-Pascal Duchemin at Thomson CSF developed the first low-pressure horizontal MOCVD reactor. So that was an important innovation that changed how we design tools. In fact, the first commercial reactor I'm aware of is this Taiyo Nippon Senso MOC reactor fabricated in 1983, I believe, for Akasaki Sensei's laboratory, but I'll have to confirm that. Another important event occurred in 1986 with the work published by Christine Wang and co-workers at MIT Lincoln Laboratories, where they did the first detailed experimental and theoretical flow and temperature studies for vertical stagnation point flow reactors. And this work showed that under proper conditions of pressure and flow rate and reactor design, you could achieve a perfectly laminar flow as shown by these beautiful linear flow rate using smokes in their reactor to show the flow patterns. Compare that to this badly recirculating vortex, which would occur under other conditions. So these major innovations, low pressure MOCVD, and the kind of work that Dr. Wang did in her team and other teams led to development in the 1990s and early 2000s of important technologies for MOCVD growth, one being the high-speed turbodisk reactor shown here, developed by EMCOR in the United States, the close-coupled showerhead developed by Thomas Swan in the United Kingdom, and the planetary rotating disk reactors initially developed by LEP in France and then commercialized by Axtron in Germany. This work in the 2010 to 2020 period expanded the size of reactors, the performance in terms of efficiency, and the quality and uniformity of the materials. So today we have extremely large reactors working 24/7 across the planet to grow these kinds of materials. In 1977, our first paper on MOCVD devices, which were aluminum gallium arsenide heterostructure solar cells, predicted that MOCVD could be used for large area 3,5 compound semiconductor epitaxy. At this time, solar cells of this kind were grown by liquid phase epitaxy on one substrate on the order of 10 to 15 square centimeters per wafer. I predicted that larger substrates could be used in the MOCVD process, larger than LPE or MBE, molecular beam epitaxy, and that it's possible that this process could be scaled for these heterostructures to greater than 200 square centimeters of substrates in a single deposition run. This was kind of a crazy story at the time because no one had a technology to make heterostructures of any reasonable size beyond about 2 inches was the limit. Nevertheless, today you can buy very large reactors. This is an example of an Axtron reactor developed around 2016, so 40 years after my prediction. This tool has a capacity for 5 200 millimeter diameter wafers, or greater than 300 square centimeters of substrate area per run, and there are even larger reactors available today. So these types of tools are not only larger, they're more efficient, and they produce better material with improved uniformity over anything that I was able to do in my small tool. Today, there are over 3,000 such large-scale MOCVD reactors in the world, making various devices, including visible LEDs and laser diodes, of course, as well as the laser sources, the VCSELs in your iPhone for face recognition. Let me now turn to our first work on solar cells and injection lasers grown by MOCVD. As I mentioned, Dr. Manasevit first grew gallium arsenide in 1968, but he did not work on devices. He was interested in chemistry. So I was fortunate to join Rockwell in 1975 and began working on using this process for lasers and solar cells. So this is our first MOCVD 35 solar cell, the first ever demonstrated. We finished this device in March of 1977. It was published in May, accepted in May, published in August. And this shows the layer structure. It's a relatively simple three-layer N-type gallium arsenide selenium dope layer, a P-type gallium arsenide zinc dope layer, and a thin 52 nanometer thick aluminum gallium arsenide wider bandgap zinc dope window layer. This composition was about 20% aluminum in this alloy. In the center panel, you see the performance of this solar cell in the fourth quadrant, showing an efficiency of about 12.8%, air mass 0, which at the time for this type of cell without an AR coating was almost that of the LP-grown standard cells. What you see in the far panel on the far right is what we consider large area wafer, 26 square centimeters. It was the largest piece of high purity, high quality gallium arsenide we could buy at the time. These were float zone crystals, and they weren't very large, but you can see this is an array of 5 by 3 1 square centimeter solar cells fabricated on a single piece, which at the time this work was done in 1979 was the record. Today, MOCVD is the dominant technology for all 3.5 compound semiconductor solar cells. This is a plot of the record solar cell efficiency at air mass 1.5 versus year for this approximately 50-year period, 1976 to 2025. Maybe hard to see, but this is 3.5 multi-junction cells, single junction gallium arsenide cells, crystalline silicon cells, thin film technologies, emerging PV, and these are hybrid systems. What you notice is that, I hope you can notice, all of the record cells today are MOCVD grown multi-junction cells. There's nothing that even comes close. And of course, there is a cost to that. They're very complex, sophisticated structures. But nevertheless, if you have to put a system in space and pay per pound to launch, you're going to buy those cells and you're going to launch them. They're also extremely radiation hardened. So yes, in space powers all MOCVD gallium arsenide today. What you see here on the left side is a picture of the Hubble Space Telescope, launched in 1990, originally with silicon solar cells. Today, everything NASA is launching in near-Earth orbit is powered by MOCVD cells. This particular beautiful Hubble system, oh, now I'm stuck. Well, we'll go back. Sorry for that. Hubble was launched originally, as I said, with silicon cells. In 2002, the space shuttle was launched to replace those cells with gallium arsenide multi-junction cells. So today, the Hubble is operating on gallium arsenide multi-junction cells, which are 20% lighter and 30% more efficient. What you couldn't see over on the right side is the Mars rovers Spirit and Opportunity. Those two Mars rovers were also powered by gallium arsenide multi-junction cells. We see now in the panel in the center is the ISS. The ISS originally had silicon cells, but now all the cells operating on the ISS are 3.5 multi-junction cells. They were replaced starting in 2000 with these MOCVD grown cells, and today the most recent ones were installed in 2023. These are the largest solar panels ever deployed in space. I'm still where I was. There we are. Okay, so there's the Mars rovers. You're familiar with them, I assume. spirit and opportunity. They're both sleeping now. Opportunity was working until a sandstorm came and covered its solar cells with dust, and so the power dropped. And now we're waiting for the next dust storm to sweep off the dust. So we'll see. 3.5 solar cells are also used on Earth. In fact, all of the record-breaking solar-powered cars use MOCVD-grown 3.5 multi-junction cells. What you see here is the winning car from the 2023 Bridgestone World Solar Challenge from Darwin to Adelaide in Australia, from KU Leuven in Belgium. And over on the right, you see a solar concentrator array that uses a 120-time magnification of solar energy onto a compact, small area gallium arsenide cell. So they're running at very high temperatures and very high photon fluxes. Let me now turn to the laser diode work that we began in 1977. While I was working on solar cells, I was also working on laser diodes because my professor, Nick Holniak, told me laser diodes are important, and I believed him. So we started to work on heterojunction lasers following the liquid phase epitaxy structure that was being manufactured, which consisted of a double heterojunction of N-type aluminum gallium arsenide, P-type aluminum gallium arsenide, and in between a sandwich layer of gallium arsenide. These devices operated pulsed at room temperature, as you can see in this panel, at about 870 nanometers. And this was a shock to virtually everyone in the field because no one thought MOCVD could make a decent device, let alone a laser diode, which was known to be quite challenging. And even though my solar cell paper appeared a few months before this, it still was a shock to people. And at some point, we moved on and started to work on the next generation of lasers, which are called quantum well lasers. So let me begin this discussion with underlying work that was done at Bell Laboratories in around 1975. The first optically pumped 3.5 two-dimensional superlattice laser was demonstrated in 1975, operated at only 15 Kelvin at liquid helium temperature. It was composed of molecular beam epitaxy-grown superlattices, which were 50 pairs of 8 nanometers gallium arsenide thick layers and 24 nanometers of aluminum gallium arsenide layers. And this thing was put in a cryostat and optically pumped with a parametric oscillator, really heavy-duty, high-power laser source, and people reported stimulated emission at this 806 nanometers, which was ascribed to quantum size effects because of the quantum mechanics of confining electrons in narrow wells. This peak is a gallium arsenide peak associated with the substrate, they claimed. Well, this got people interested because it looks like we could create a new type of semiconductor designed by ourselves to have a different band structure following the work of Leo Isaki and others more at IBM. So, interesting question is, how do we make the structure by any process other than MBE because it was so expensive? So the question became, is there any other way to make these ultra-thin layers to realize devices that use the quantum size effect? The answer was, from my advisor, Nick Holniak, the crystal doesn't know how it's grown, so let's just give it a try. So he and his students used liquid phase epitaxy to grow very thin layers. Not only did they grow very thin layers, they grew them of the quaternary, indium gallium phosphide arsenide. So this was no small feat. Bell Labs was growing thin gallium arsenide layers, and the students at Illinois were growing thin quaternary layers, an entirely more difficult prospect, and again by LPE, but showed quantum size effect in their lasers only pulsed at low temperature, 77 Kelvin. So these didn't operate at room temperature. They had 20-period quaternary quantum size effect laser diodes. Here's a picture of the students, Ray Chin and his colleague Ed Brezik in their laboratory. Notice this reactor chamber. This is a simple university LPE reactor with a handmade furnace, and they were able to compete with Bell Labs' MBE equipment. Sort of amazing. Well, NIC's first quantum well laser diode was reported as a late newspaper at the IEEE Device Research Conference in late June 1977. Our first MOCV laser, double heterojunction laser, was reported at the same conference as another late newspaper. And before the meeting, Nick and I had an informal meeting where we shared our new results, and we decided to collaborate on making quantum well laser diodes. So we started working on this right away when I got back from the conference, and 4 months later, in November 1977, we demonstrated the first quantum well laser diodes, and they operate at room temperature. I want to mention that the first MBE-grown quantum well lasers were not demonstrated until 18 months later by Wan Tiansang at Bell Labs. So how did this happen? Well, by then I had a third-generation reactor, shown here, that was computer-controlled. So this is probably the world's first computer-controlled MOCVD reactor in the known universe. It doesn't look like much, but it made really good lasers at the time, record-breaking lasers and record-breaking solar cells. So here's our results from that work, published in March of 78, but submitted, as you see, in November 77, showing room temperature operation of quantum well lasers. These devices had a single quantum well, so the entire gain region was just one quantum well, unlike the 40 or 20 pair quantum well lasers reported earlier. And you can see very strong quantum size effects because the emission shifts from around gallium arsenide to high energy and higher quantum states as we move. Oh, my batteries kaput. As we move to higher energy. So in this next period, we developed quantum well laser diodes in many different ways, beginning in 1977 with the first double heterojunction lasers with gallium arsenide active regions, pulsed at room temperature. Then the first MOCV lasers with aluminum gallium arsenide active regions emitting at shorter wavelengths. Then in 1978, the first double heterostructure lasers operating continuous wave at room temperature. And also in 78, the first MOCV laser diodes with non-planar active regions. The first quantum well optically pumped lasers at room temperature. First quantum well laser diodes at room temperature. First continuous wave quantum well laser diodes in 1979. First graded index quantum well laser diodes. First laser diodes with distributed Bragg cladding layers. First MOCV lasers with useful operating lifetimes. And when I joined Bell Laboratories, eventually we, in 1983, demonstrated the first long-lived MOCV-grown laser diodes with lifetimes greater than 10 to the 6 hours. In 1985, we reported the first 1.5 micron indium gallium arsenide phosphide double lasers grown by atmospheric pressure MOCVD. So in this span of a few years, we established that MOCVD was a dominant technology for laser diodes, and in particular this event with long-lived laser diodes really set the stage, I think, for commitment to grow high reliability lasers by MOCVD. Today, of course, things have improved dramatically over those early works, and in the last 3 decades, the average power of a quantum laser has increased exponentially, while the average price has decreased exponentially, opening up many new applications for coherent light, as shown in this graphic. Laser diodes for display illumination, data storage and communication, defense, material processing, optical sensing, healthcare, optical pumping. And 2 of these in particular, display illumination and optical sensing, have developed important technologies for 3D sensing and imaging, which impact the technologies for smartphones, tablets, virtual reality, smart home, Internet of Things, automotive and drones, gaming, TVs, PCs, and notebooks. The MOCV laser diode market continues to grow rapidly, beginning in 2018 at about $4.5 billion, increasing to $10 billion this year in 2025 and projected to 14 billion in 2029. As you can see, the large applications for these devices are optical sensing and data storage and communications. And those segments are dramatically going to increase as the Internet of Things and artificial intelligence are developed further. Let me now turn to the light-emitting diode technology, which sort of began, as I mentioned, with the visible LED that Nick Holonyak developed in 1962. Shown here is a timeline of the performance of a visible LED versus year for the 50-year period from 1960 to 2010. The vertical axis is a log scale of luminous efficacy in lumens per watt, and of course year along this axis. The general trend of this development is about 10 times performance per decade increase. Interesting points are that Thomas Edison's first light bulb was about 1 lumen per watt. The typical unfiltered 60-watt incandescent lamp is about 20 lumens per watt, and the typical white fluorescent lamp in a linear tube is about 85 lumens per watt. So it took a while before an LED could make it to compete with a fluorescent lamp. Actually, if you look carefully, something dramatic happened at this time frame around 1986 or 7, and everything on this side of this plot is either vapor phase epitaxy or liquid phase epitaxy. Everything on this side of the plot is MOCVD. So everything that drives this performance up is all MOCVD, including, of course, the important nitride work that began here in Japan. So this is a technology divide that occurred around 1987. Another important divide that I've identified is this one, where everything on this side of the dashed dot line is quantum well light emitting diodes. So all of these performance advantages were obtained with quantum wells. What you see here is an important event. This is the first commercial white LED made by Nichia in Japan at about 5 lumens per watt in about 1996. The first high-performance white LED that could compete with a fluorescent tube was developed in 2006. So it took a while before we could get rid of that fluorescent tube and the mercury contamination that is associated with that product. So MOCVD, as I mentioned, began around 1968. It took about 19 years to become the dominant technology for LEDs. Quantum well laser diodes began, as I just showed you, around 1978. It took 14 years for that to become the dominant light-emitting technology for LEDs. So overall, about 44 years of development to make current generation light-emitting diodes. An important fact I'd like to emphasize is that in 1995, when Professor Holonyak was giving his talk to the JapanPrize people, he predicted, he pointed to the ceiling and said, all of this is going to go. All of the fluorescent lighting in this room is going to go. And that was a year before Nichia announced its first white LED, and 20 years before you could actually do that. So it was very, he was very gung-ho on LEDs, obviously. Another important event occurred in 2006, namely the 80th birthday of Queen Elizabeth II. And to celebrate that, the royal household asked Philips Lumileds to illuminate the facade of the Buckingham Palace with white LEDs. So this is the year that the fluorescent tube got outperformed by LEDs, and it's the same year that Buckingham Palace became lit by LEDs externally as well as internally. And at that time, the cost of illuminating Buckingham Palace at night was $2 per night for electricity. So maybe the Queen got a discount on her electricity, I'm not sure. The global MOCVD lighting market continues to grow. It's worth around $70.5 billion go back again, in 2022 and growing, at a compound annual growth rate of about 11.3%. And all of these devices are grown by MOCVD. All of this market share is by MOCVD. Another important application is the intergalactic network. Some of you may know that as the Internet. Its actual official beginning name was the Intergalactic Network. And it was developed in the 1960s. And it became public in 1993. This plot shows the number of Internet users in the world versus year, and obviously rapidly increasing recently. And in fact, the first billion users were online by 2005. It took 12 years from the opening of the Internet to get to the first billion users. Second billion in 2010, so 5 years. The next billion, third billion in 2014, so 4 years. The next billion, or the fifth billion in 2022, and COVID, so that was a 5-year period. COVID came in, and now we have only 3 years for the next billion, and we're at about 15.3 billion users now. So all of this development would not have happened without MOCVD lasers and detectors and photonic integrated circuits that now underpin the Internet. So about 30 years of development has led us to where we are today on the Internet. An interesting point is that a lot of time is spent on social media, and this is from January 2021, showing the daily time spent using social media versus country, ranging from about 4 hours and 15 minutes a day for the Philippines to only about 51 minutes a day for Japan, and an average of 2 hours and 25 minutes in the world. So Japan's about 35 minutes below the average use of personal social media. The MOCVD devices that power this expansion are both on land and in the ocean. This is a representation of the many optical fibers that are on the ocean floor. They've become critical systems that depend on MOCVD devices for performance. And most of the world's undersea data cables are data cables, and more than 95% of all Internet traffic travels along them, making MOCVD a key technology for this telecom expansion. An important example of how MOCVD empowers the developers to make complex circuits is the photonic integrated circuit, shown here schematically. These are MOCVD-grown indium phosphide-based photonic integrated circuits that contain typically 10 to 100 laser diodes on one chip with modulators and drivers. And you can see some pictures here of the early ones from Infinera. The market growth is expected to accelerate with about a 20.5 compound annual growth rate. The current size in 2021 was about $17.6 billion. By 2030, it'll be $41 billion. North America had the largest market share of MOCVD-grown PICs with greater than 45%. And it's expected to be driven by the improvement of data center use, also, of course, quantum computing and artificial intelligence, as well as telecom and more conventional applications, including potentially autonomous vehicles. Let me now turn to power device applications for MOCVD-grown devices. This is a relatively newer application space, but the 3 nitride materials offer advantages over traditional silicon-based and silicon carbide-based power devices, making 3 nitrides highly suitable for various EV and power supply applications. The 3 nitride materials offer higher efficiency because GaN devices have higher electron mobility, which allows for faster switching speeds and reduced energy loss. They have compact design capabilities because they enable lightweight power electronics because of the size, weight advantages for these smaller systems, making them better choices for compact systems, especially in electric vehicles. They offer better heat dissipation as well because the gallium nitride and its relatives have superior thermal conductivity, improving heat management and reliability, and they offer higher voltage operation than silicon, which is beneficial for EV. So here you have some car-based applications. This is a computer power supply, and this is even a small-scale power converter, all of which now have gallium nitride technology grown by MOCVD. Let me now speculate on the future impact of the MOCVD materials technology. This shows the 1960 to 2030 inflection points of each compound semiconductor materials and device technology and its outlook. You can see, of course, we've included gallium arsenide, indium phosphide, and gallium nitride-based technology, and silicon carbide is a compound semiconductor, of course, but not a 3.5. One thing I want to point out is that except for this early gallium arsenide-based LED inflection point, all of these inflection points rely on MOCVD technology. And in fact, this prediction of GaN in a vehicle around 2030 is wrong. It's actually in a vehicle now. Let me turn now to what I think the future of electronics will probably look like. We all realize that Moore's law is coming to an end. In fact, it has already ended, really. Miniaturization of silicon devices is becoming more difficult and extremely expensive, requiring extreme UV lithography. Power requirements for input and output functions are creating design barriers, and new, more powerful semiconductor materials and processes are required. So my belief is that the solution to these difficulties is the integration of 3.5 compound semiconductors with silicon systems based on MOCVD integration with CMOS, creating system on integrated chips, or what is referred to as SOICs. My point is that Moore's law will not be viable without MOCVD. This plot is from TSMC. It shows a semi-log plot of the density per square millimeter versus year for various technologies. And they point out that this part of their development, which is beginning basically now, is relying on system on integrated chips. So right now they're integrating multiple silicon chips along with some 3.5 chips, and that is being designed primarily to manage the I/O power problem using optical interconnects. So here's a concept for the future of an SOIC with the integration of MOCVD 3.5 devices and silicon-based integrated circuits with multiple functions being incorporated into a silicon CMOS foundry by attaching MOCVD-grown epitaxial structures with device functionality that silicon cannot match. So this is my young lady that is competing with the elephant in the room. Finally, I want to close with a remark from Nick Holonyak, who was interviewed in 2014, and he was asked, what is the future of 3.5 LEDs? Holonyak's response was, it's in its infancy in the sense that it can go a long, long way further. We're still searching for better ways of making the crystals, doing the chemistry, getting everything right. Well, today, after 58 years, we're still working on getting everything right for MOCVD production, but we made a lot of progress, thanks to many people in this room. So let me close with the Swiss Army knife. Again, this is my claim. The MOCVD is the Swiss Army knife of 3.5 epitaxy. Domo arigatou gozaimasu.